Hello, and welcome to the presentation for the volume of the rectangular prisms and triangular prisms. The rectangular prism is just a fancy way of saying a box. It's a three-dimensional figure that you can put stuff inside, and we're going to begin looking at the volume of this. So if you haven't done so already, please go to the Google Classroom and do the Do Now. In the Do Now, we have helps me to take attendance, helps me to get information to you, make sure that you understand the objective, all that. So today, we're going to be looking at using Edpuzzle for our lesson. So we're going to be using it through the concept of volume, which is our next topic that we're going to be looking at for our unit. We're going to begin the standard for the volume. And we're going to be using Edpuzzle just to help us to understand what we need to do for our for our concept. So today all we're going to be doing is learning the new material, and then tomorrow we're going to be doing the practice problems for the volume and rectangular and triangular prisms. Okay, so there's about 4 videos that we're going to be doing. They're all little clips of them, and we're going to be talking about the various parts in here. And so this first one helps us to understand what is a prism.
What is a prism? A prism is a solid figure that has parallel and congruent bases that are both polygons. So here we have an example of a prism. Let's take this prism and identify the 2 bases. Remember, to identify the bases of a prism, we want to find 2 identical polygons. So let's look. Here we have a polygon right here. It's in the shape of a pentagon. And here's another pentagon right here. There are 2 identical pentagons in this prism. Those 2 pentagons are the 2 bases of this prism. So now we've identified the bases of this prism. Great! Now let's name this prism. Prisms are named for the shape of their bases. Our bases are shaped like pentagons. So this prism would be called a pentagonal prism. Cool! Now there are many different types of prisms. Here are 2 more types of prisms. Let's look at each of them. Here, we have 2 bases again. This one and this one. They're both shaped like triangles. So, we have a base here and a base here. These 2 congruent triangles are the 2 bases of this prism. And since our bases are shaped like triangles, this is called a triangular prism. Now let's take a look at this prism. Here we have a rectangle, and here we have another rectangle. These 2 rectangles are the 2 bases of this prism. And since our 2 bases are shaped like rectangles, this is called a rectangular prism. So remember, prisms come in all different types. In order to have a prism, you must have a solid figure that has parallel and congruent bases that are both polygons. And you name your prism for the shape of its bases.
Okay, so now you get the idea of what we're looking at in here. For our prism, it is a 3-dimensional object that we often try to put on our paper, which is 2-dimensional, but we can do and put those different values, and we're going to calculate the volume inside of it. So this guy's going to tell us about the volume.
Hi, I'm Rob. Welcome to Math Antics. In this lesson, we're going to learn about another important geometry quantity called volume. Specifically, we're going to learn what volume is, and what kind of units we use to measure volume, and how we can calculate the volumes of a few simple geometric shapes. The first thing you need to know is that volume is a quantity that all 3-dimensional objects have. But to understand what it means, it will help if we back up just a little and start out with a 1-dimensional object, like this line segment. To measure a 1-dimensional object, we need a 1-dimensional quantity, which we usually call length. The length of this line happens to be exactly 1 centimeter, which is a common unit for measuring length. And in the Math Antics video about area, we saw that if we move or extend this 1-dimensional line in a direction perpendicular to it by a distance of 1 centimeter, it forms a 2-dimensional object called a square. 2-dimensional objects are measured by the 2-dimensional quantity that we call area. Because the original line was 1 centimeter long, and we extended it a distance of 1 centimeter, the amount of area that this square occupies is 1 square centimeter, which is a common unit for measuring area. Okay, now imagine that we take that two-dimensional square and move or extend it in a direction perpendicular to its surface by a distance of 1 centimeter. It forms a three-dimensional object that's called a cube. And to measure a three-dimensional object like this, we use a three-dimensional quantity called volume. Volume tells us how much three-dimensional space, or 3D space, an object occupies. Alright, but how much volume does this cube have? Well, since it was made by extending 1 square centimeter, a distance of 1 centimeter in the third dimension, we say that its volume is exactly 1 cubic centimeter, which is a common unit for measuring volume. So square units are used to measure area, and cubic units are used to measure volume. Since square units are made by multiplying two one-dimensional units together, like centimeter times centimeter, we can abbreviate them using the exponent notation, centimeters to the second power, or centimeters squared. And since cubic units are made by multiplying three one-dimensional units together, like centimeter times centimeter times centimeter, we can abbreviate them using exponent notation, centimeters to the third power, or centimeters cubed. And just like there were different sizes of square units, like square inches, square meters, or square miles, there's also different sized cubic units, like cubic inches, cubic meters, or cubic miles. See how area and square units are related to volume and cubic units? And there's another similarity too. Do you remember how you can use square units to measure the area of any 2D shape, not just squares? Well, you can use cubic units to measure the volume of any 3D shape, not just cubes. To see how that works, take a look at this 2D circle and this 3D object called a sphere, which is like a ball. Just like you can use a bunch of small squares to approximate the area of the circle, you can use a bunch of small cubes to approximate the volume of the sphere. And here's the really cool part. The smaller the squares you use, the closer their combined area will match the area of the circle. And the smaller the cubes you use, the closer their combined volume will match the volume of the sphere.
Hey everyone, welcome back to Mashup Math. Anthony here. Thank you for joining me on this lesson. We are going to explore right rectangular prisms, how to find their volume, and what to do when fractions are involved. You ready? Hey guys, welcome back. We're going to start off this lesson on finding the volume of right rectangular prisms, which is a shape that we're all familiar with when we get those Amazon packages in the mail. That box is a right rectangular prism. And we are going to think about these kind of figures in terms of their volume. Now, the volume of a rectangular prism is going to be dependent on its dimensions, in other words, its length, its width, and its height. So, for example, let's consider a rectangular prism with a length of 10 inches, a width of 4 inches, and a height of 7 inches. Now, we should have a basic understanding that the volume of a figure is a measure of the amount of space inside of that figure, or how much it can hold inside. Now, you may also know that in geometry, we express volume in cubic units. So, in other words, the volume represents the number of unit cubes it would take to fill the entire prism. And since the length, width, and height of the prism shown is measured in inches, our unit cube will have a length of 1 inch, a width of 1 inch, and a height of 1 inch. So if we were to take our rectangular prism and completely fill it from bottom to top with these 1 inch unit cubes, and then counted the total number of cubes, that final total would represent the volume of the figure. Now, counting every single one of these cubes would take a very long time and is not the most efficient way to find volume. Luckily, rectangular prisms have certain properties that allow us to apply general rules for finding volume, and we're going to explore those rules now. So let's imagine that we only use those 1 inch unit cubes to fill the bottom layer of this rectangular prism. To fill this bottom layer, we would need 10 cubes along the length and 4 cubes along the width. So basically, we would have 4 rows of 10 1 inch unit cubes. So to figure out the total number of 1-inch unit cubes to cover this bottom layer, we can just multiply 10 times 4, and our product is 40. So we have 40 cubes comprising this bottom layer of the rectangular prism. Now to determine how many of these 40 cube layers it would take to fill the entire prism, we have to look at the height, which is 7 inches, which means that we would need 7 layers of 40 cubes. So by multiplying 40 times 7, our product of 280 represents the total number of unit cubes it would take to fill this entire prism. So now we can conclude that the prism has a volume of 280 1-inch cubes, or 280 cubic inches. So now let's go back to thinking about some of those general rules that apply to finding the volume of a rectangular prism. So in that last example, we found volume by first figuring out the number of cubes in the base layer and then multiplying that value by 7, which represented the height of the figure. Now to find that number of cubes in the base layer, we found the area of the base, in this case the length times the width, or 4 times 10, and multiply that by 7. Now 7 again represented the height. So we can conclude that we can define the volume of a rectangular prism by multiplying the area of the base by the height.
Cool.
And thinking about volume in this way should help us to better understand the more familiar formula for finding the volume of a rectangular prism, which is length times width times height. So in this case, that letter B, that base, represents the length times the width. So now moving forward, understand that you can use either formula for determining the volume of a rectangular prism. So now let's go ahead and try another example of finding the volume of a rectangular prism. Now in this case, our units are centimeters, so we want to figure out how many 1 centimeter unit cubes it would take to fill this figure from bottom to top. So let's go ahead and use the volume equals length times width times height approach. So in this example, the length and width are represented by 7 centimeters and 2 centimeters, and the height is represented by 5 centimeters. So our next step is to substitute these values into the equation and then multiply. Now the product of the length and the width, 7 and 2, is just 14, which represents the area of the base, multiplied by the height of 5. And our product represents our volume, which is 71 centimeter cubes. And again, we can visualize this as 5 of those 7 by 2 base layers stacked up from bottom to top.
In this video, we're going to explore where the formula for finding the volume of
So we're going to get in here, we're going to look at the volume of a triangular prism.
a triangular prism comes from. First, we're going to back up and look at the volume of a rectangular prism that we discovered in a previous video. Beginning with the base, we'll attempt to find the area using length times width. And since we know for any prism we can find the volume by multiplying the area of the base times the height, we can see that the volume of a rectangular prism can be found using the formula length times width times height. The volume of a triangular prism can be found in a similar manner. By diagonally dividing the rectangular prism down the center, we will actually get 2 triangular prisms. Since we've essentially cut this rectangular prism in half, it makes sense that we've actually cut the base in half, and thus we're going to have to cut the formula for the volume of a rectangular prism in half as well. And thus, we'll get the volume of a triangular prism, which is the length times the width times the height